Welcome everybody to Lecture 6, Databases and Information Systems in the winter semester 25-26. Today's lecture is about indexing, query optimization and a little bit of ACID. It's a completely new lecture. It was extreme amount of work for myself and Robin and myself. So we hope that you like it and appreciate it, but we are sure there will be some errors, so please excuse those and enjoy the rest and tell us if you find any errors. So here's an overview. As usual, I will say something about the experiences with the last exercise sheet first, which was about joins and more SQL. And then today we will talk about indexing, in particular the index B plus tree, query optimization. I will tell you all about it, and a little bit of ACID, but that will just be in the end and just for information. And the exercise sheet will be, we will explain what query optimization is, and you will just do that by hand on a given example, and then integrate it into your system, and I will show you what that means in a minute. So, excerpts from your feedback for the last sheet. Again, the lecture and the sheet were really nice, a great exercise that helped to deeply understand the concepts. It was a little bit harder, very fun sheet as always, but the manual query planning makes my head hurt. Yeah, that's what this lecture is about. So in the last lectures you did the query planning, you just wrote the query plan in code, right? Do this with these two tables, write the result in a variable, do it with this, then group by, then join, then select, then project. This lecture is about doing this automatically, and the question is how to do that. I enjoyed the lecture, but found the exercise sheet harder than usual, mainly to understand grouping with multiple columns. We weren't expecting that, but several people wrote that the group by, I don't think the group by was really hard, but maybe, let me go there very briefly maybe, and this was the last. I think what was hard, let me just go to the slide, and I will tell you when, I mean, group by is not really hard. So here's the group by. You have something, you have a table. So in this case, you group by year. So you have something on which you group, and this is one column in this example, but can be many columns. And then you have the things on which you do not group, but which you aggregate. So you have the thing on which you group, which is a subset of the columns, and then you have some columns on which you do not group, on which you aggregate, and you do something different for every column. And just the interface for this was, I think, hard to understand, and for some of you, and I think that was the reason. If it was something else, please tell me. But I think that was the reason. Understanding the interface, once that is clear, I think it's not hard. So here's another comment. I really struggled with the execute method for group by. The sheet was very hard and I did not have enough time. I think it was mainly about not having enough time. And I like that instead of switching between slides and editing mode to fix a wrong font style, the assistant just takes note of it. Yeah, I realized that too. One or two errors I can fix, but if I do it like every slide, it's annoying, even for myself. So we changed that. And sorry for all the wrong typos and fonts and things which are black, although they should be blue. What does it say about humanity? Deep philosophical question that the most used relational database management system in the world has neither a hash nor merge join, which is really true and quite amazing. That they avoid algorithms and data structures at all costs. It's a very good comment. I think it's true. I already told you the inventor and maintainer, I don't think they heard a course like this one. People just start out with something that works for now, then it becomes too much of a hassle to replace it. I think that's a very appropriate comment too. People are looking for stuff that just works, even if it's slow or uses gigantic amounts of RAM or something. At least it's ease of use is, I think, number one for a lot of people. easy to use, even if performance is abysmal. That's really interesting. As long as things work, humans don't feel the need to change it. People care about practicality, so there were a lot of comments in this vein. The obvious way is not the best in all situations, exactly true. So SQLite is really, let me do it the obvious way, which is good enough for simple data, not so much data, but of course there are better ways to do it. And then there was a very long comment which somehow replied to the philosophical nature of the question. I'm abbreviating it, so excuse to the person who wrote it, but the gist of it was that, so SQLite apparently is made for small data and individual purposes, so not really. Individuality leads to a lot of problems in the world today, such as climate change and poverty. So once the most used database engine in the world has a hash join and a merge join, we know that humanity is saved. It was a long logical inference, which actually 10 points, but it was actually quite good. And this is, I think, the gist of it. So that's it about the last lecture in sheet. We'll go back a little bit. 2 parts, indexing and query optimization, automatic query planning. First, the indexing. There's a lot to say about both topics, and we really try to distill it to the core, which was not easy because one can have about each of them 3 lectures or a whole course. So just the core of it, motivation. So we have seen joins. Last lectures were all about joins, and not only last lectures, but relational databases. The main operation is join. So speeding up joins is really, really important in practice and in this lecture. And we can speed it up by pre-computing something that's called an index. And you do it like this. And an index is not for a whole table, it's for a column of a table. And as usual, SQL is easy to understand, and the simple commands create an index for this table, movies for this column. Column movie ID of table movies. And then I give the index a name, movies index. I don't really need the name later, except if I want to delete the index or list all indexes, because the system will use it automatically. And another one, create index on the table persons and the same column. So now I have 2 columns where I've created an index, and the next slides will be about what that means. What did I do now, creating an index? First, let's just do it with SQLite, and I've prepared something here. So these are our table. You have worked with them for 3-4 exercises. Now, let me maybe, let me show one of them. Persons TSV, for example, was this, just all kinds of actors. And so here we have Steffen Gräbner, I don't know him, has this ID and this birth date, plays in some movie. This is used in other tables. Let's maybe also look at the movies table once more, so that you know what the data is, because that was the movies. It had the ID of the movie, the title, the year, description, IMDb score, votes. You know all of that already. That's 1 line per movie, and the rest is just scrolled away to the right. This was our data. And now let's look. I wrote a little script here, movies SQL, which just reads, it creates all the tables. This is nothing new or surprising. Movies, roles, directors, persons, awards, names of awards. These are 2 separate tables because one award can have multiple names, and then you always have to separate it. We just import it. Let's just, for now, test it here. Okay, now we've just imported it and done nothing with it. And now Robin, can you confirm that timer on just measures from that point onwards?
It works for each individual query.
Okay, it works for individual queries.
Each query you run reports its time.
Okay. So for each operation you mean?
Yes.
Okay, that's a good one. So So I wasn't sure about that. Let's switch on the timer here, timer on, and then after every individual operation I do, I should see the running time. So here I'm saying create index. This is just what was on the slide. And now I should see 2 timings, 1 for each. Yeah. So that's the time. So it took 3 milliseconds to create this index, 21 milliseconds to create the other index. The one was on movies. Let's maybe briefly check the size of movies. That's not so many movies. And the roles, yeah, that's 10 times larger, and it also took significantly longer. So just look at the real time. The rest is system internal stuff. Okay, and now let's run a query with these indexes, and let's just do a natural join on movies and roles. So movies and roles is what roles were played in that movie. Natural join means if there are 2 columns with the same name, join on them. Let's maybe, just so that this is super clear. So movie has movie ID here, and roles should also have movie IDs. Yeah, it also has a movie ID and then the person ID and which role they played. You should know all that. And let's just do the same thing again. I'm not creating. Yeah. So now it took 2 milliseconds to create this index, 22 this, and now it took 9 milliseconds to answer the query. And it's just a count query. It doesn't output the result. I don't want to clutter the console. Just want to know, okay, 70,304 lines. Let me do the same thing with just without the indexes. Okay, and now you see a difference, right? So with the indexes, it was faster. And yeah, more than 3 times faster. Let's maybe do some other small experiments, and then we go back to the slides again. Let's just create 1 index. Now I just created 1 index. Now it's almost as fast as with both indexes. Let's create the other index. Okay, and not delete the C. Okay, yeah. So now it's even faster than with both indexes, which is really kind of strange. Okay, but I have something on this on the slide. So this is something for you to play around with as well. And there's one thing we could do, and then we had this explain query graph, right? Let's just do that. I'm not executing this now, but just, do I need the time? No, I don't want the time anymore. You have seen that. Let's just, okay, explain query plan, not query graph, sorry. There was this internal explain, okay. Yeah, so here it says scan movies, so that's a natural join, search roles using covering index, roles index, movie ID. So it's using that index, right? So we see it here, it's using that index. And if I have 2 indexes, let's see whether it's using 2 indexes now. Now it has to choose which one to use, and we will see in a minute what that means. Now it's using the other one, which is maybe was a bad idea because using that one is better, but we will see in a minute. But it's not using, it's using both. Okay, that's interesting. It is using both. But it's using one for scanning and one for searching. Okay, you have seen some things, now let's go back to the slides. And feel free to play around with it yourself. As you can see in SQLite, it's very easy. So it's faster with indexes than without. It's not faster if you use both indexes instead of just one. Actually, it was the fastest when you use one particular index and not the other, which is kind of strange, which SQLite is in certain ways. So, B plus tree. This is what, spoiler alert, what SQLite computes. B plus tree, more specifically an index B plus tree, and I will explain tree, B plus, and index in the following. Thank you, Frank. And sound is working better today. So the input is like create index command. Here's a table, and here's a column which I want to index. And the column should have something which is sortable, so total order. We will see an example in a second. this is easy to do. You can also create an index for 2 columns at once or 3. We will not do that here, but if you think about it, it's easy to generalize. An index, there's something called a search tree. I will not go into all the details of a search tree again, but even if you have never seen a search tree before, you will understand it. If you have seen one before, this will be super clear immediately, but it's also fine if you haven't seen one. It's a tree, and one with a higher degree, D, so not just a binary tree, but you have, nodes can have more than 2 children. And it has the following properties. I will go over this quickly so that we can jump to the example very quickly. So each leaf at the bottom of the tree has up to D pairs. There's a pointer from one leaf to the next, so the leaves are chained in sorted order, and we will see that. And the inner nodes have children, and they store something about their children, and we will see what, so that you can search in the tree. And let's just, so here's an example, and let me actually start from a table. So this is a table, very simplified: movies, title, year, rating. It's not sorted deliberately. And let's do one thing before I go to the next slide. The first thing I now have to do is sort this somehow, and I want the rating column. So let me write the row indices here, and now you have to help me a little bit. So now what I want is, I want the pairs, let me write this here, pairs of value. So value is the rating, and row index in sorted order, sorted order, and sorted by value. Okay, and let's do that. What's the first one if we sort ascending in ascending order? So the smallest one, smallest value? 7.9, that's correct. And I do one more thing, and I will not switch. Which row index is it? 4, exactly. So I will write it like this, 794. And now let me not write the row index each time, but let me first write all the ratings. What's the next rating? You have to help me. You have to sort live now. 8.3. What's the next one? 8.5. What's the next one? 8.7. What's the next one? 8.8. Okay. I'm trusting you. Next one. 9.0. Oh, I'm running out of space. Which next one? Oh my, I'm running out of space. Is there also a 9.2? And also a 9.3? Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. I was not economic with my space. Now the column indices. Which one is it? Here? 6, here, 2, yes, exactly, 1, 7, 9, and 3, and 5, right? Okay, and as you, so the orange numbers should be a permutation of the row indices. That's what sorting does. It permutes it in a way. Why do I need that? Well, the result of the join will tell me something like, yeah, here's the match, and then maybe I want the whole row, so I need a way to get to the row. That's why I store the row indices. And should I store the row indices or the whole row? We will come back to that. So, and that's just, so it should be exactly the same thing what we have just computed on the previous slide. I hope it's correct. And this is just the leaves of my index B plus tree with, and I should say with D equals 3. Let me just put that here. Yeah, so D equal 3. So I have three things, so that's one leaf, that's one leaf, and that's one leaf. And also what I've not drawn here automatically, they are chained. So I have pointers from here to here. And this is so here I have an inner node, so let me also just clarify that. So that's, this is a leaf at the bottom of the tree, and this is an inner node. Inner node is just everything that's not a tree. And now, well, I have a pointer here that points to 3 pointers, which point to my 3 children. So I have 3 children in this tree, and this is just the smallest value in the second child, and this is the smallest value in the third child. I'm not storing the smallest value in the first child, so in the first leaf, just so if I have D children, 3 children, I just have 2 here. So this is, and let me just maybe show that. So this exactly corresponds to this. This is no coincidence. And this exactly corresponds to this. And I'm claiming if you have this, then you can use this for searching. And we will do that in a second with a little more complex tree. And now it's not ratings anymore because they are too wide. I wanted to have something with 2 levels. And I'm just writing. So again, the origin number, now assume it comes from a table with 22 values. I hope that's correct. It should be 1, 2, 3, 4, 5, 6, 7 times 3, 21 plus 1. Yes, 22. I have 1, 2, 3, 4, 5, 6, 7, 8 leaves. Of course, it does not have to be divisible by 3. So here I have one which just has 1 and not 3. This can happen. For simplicity, we're not what happens if I have the same number here. Let's just forget that for now. I will briefly come back to it in the end. And now I have some inner nodes here, and the inner nodes always have at most, so this is again D equals 3. So let me just write that here. It's again the D equals 3 case, so at most 3 in a leaf, and at most 3 in the inner node, 3 children. It's the same thing. And also, so the blue things are in sorted order, yes? And this is 8. This is, let me also do that again, so that it's absolutely clear. This is this 8. This is this 14. This is this 28. And this is this 39. And this is this 72. And now I have another layer, so it should be a tree, so always a single root node. And so this should now be, this is not what I wrote, was not correct. This should be the, the 21 is in the, is that, I think that's what I want, yes? This should be this. So in the subtree, so not in the child, I was imprecise there, and this is the smallest one here. By the way this is done, and I don't have a lot of time to go into this, everything here except the very smallest value will be also stored in one inner, nothing will be duplicated here. So this left thing here is stored in this one, but not in this one. You can think about it. Let's just try to do a lookup now and see if this works. So let's look up, what do we want to look up? Let's look up 34. Let's do a lookup, and maybe not in red, because I've used that already, 34. And let's maybe do it in wonderful green. Lookup of 34. So I just want to know, is 34 in my table? Why do I want to look up? We will come back to that. So I'm doing a lookup of 34. Now I'm checking, I'm checking 34, is it smaller or larger than 21? I'm also checking 34 smaller or larger than 53. And I think you get the idea just by looking at these. That's also why I wrote it that way. I can deduce that if it's in the tree, it will be down here. Okay? That's what a search tree does. Now I do the same thing here, and as it so happens, it's again, so I'm comparing. So if it now would be something smaller, I would go here. If it's larger, I would go to the right. So that's also why 2 values are enough. I just need to decide in which of the 3 children I continue. So I'm asking that question here. And it's, let me put a question mark here, 28, and I'm also asking this here, 39. And actually, if you imagine if there are a lot of keys here, I can do a binary search even. I will come back to that. For now, let's just go through them one after the other, and then go here. And then here I can do a binary search in this child. So a binary search here, and I can conclude that it's not found. So that's the result in this case. And just to recapitulate, so what I'm doing here, I'm just checking these inner things here, and I can say with certainty, if 34 in the tree, it will be here. It can't be here because everything here is less or equal than 21, because 21 was the smallest of this thing. And it can't be here because everything here will be greater or equal to 53. So if it's in the tree, it will be here. Same here. If it's in my tree, I'm sorry, it will be here. And now I'm in a leaf and I can be sure if it's there, it will be here. So I just search it here. Either I find it or it's not there. That's the principle of a search tree. And this is already a more sophisticated search. The typical search tree is just binary with 2 children. And I will tell you in a minute why you have a bigger degree for databases, but is the principle clear? That's the B+ tree. Any questions about this? Yes?
What does the P1, P2, P3 stand for? That pointers to the other.
Yes, let me write that. It's the pointer. It's just to clarify that I have to store the pointer. Let me just, so PI pointer to the ith child. Sorry, so like humans, you have pointers to your children. Otherwise, you cannot access them. So, any other questions? Yes?
Is there a B tree?
Yeah, there's a B tree, and not only is there a B tree, there's also a slide about the difference between a B+ tree and a B tree. But just to keep the suspense up, I have it's towards the end of this. It's slide 8 of 8. Any other question? Yes, please.
We had 1 item less. Would the last group of 3 be 1 level higher?
If we had 1 item less, I think then it would still, then we would just have 1 pointer here, right? So your question is if this would not be there, which is a very good question. The thing is, we can have at most 3 children, so we need something here, right? So even if if we only have 3 here, we need this inner node, and it's a bit sad because it doesn't do anything useful, but it will be there in case new elements come. We will talk about updates too. So yes, so even if I have just 1 here, I will need this inner node, because otherwise the constraint is nothing here can have more than 3 things. Yes, please?
And what do we write instead of the 72 then? If the last thing is missing?
Nothing.
No, it is.
So basically this inner node it just serves as a proxy, because it just has 1 child, right? So I'm searching something, it just says, yeah, please. Nothing to see here, just go on. I mean, the point of these things is if I have more than 1 child, I have to tell you where to go on searching. If I have just 1 child, there's nothing to do. So this inner node is having holiday time until it gets more. For lookup, so there's a question in the chat. For lookup, this is not better than a binary search in a sorted list, right? So this is only better for insertion. Okay. the question is why. That's a good comment, and we'll come back to this. For lookup, why do I even need this? I could do binary search in this whole thing down here. It's a very appropriate comment. Why do I even need this thing on top here? I could do binary search in this thing at the bottom. Just store this thing at the bottom. Actually, the next slide is about, or the one after that, about the complexity. So I will reply to that. And it's actually this slide. So we are still B plus tree, degree D, n. So n in this case is 22. So the number of things which are stored. And I say, and this is exactly the question in the chat, this takes log n time. Why does it take log n time? So in each inner node or leaf, I need log 2d time. Why? Let me just write that here. That's because binary search. Binary search in D elements, right? In every inner node or leaf, that's how the thing is constructed. I have at most D things, they are sorted. So binary search. The depth of the tree, it has degree D, log D of n. This is not algorithms and data structure, so I'm not computing this here. So it's log dn, and to be more precise, it's the ceiling of this. So let me just write that here, because this is the other thing is a fractional number. And let's just do a little math here. If I multiply the two, so in each, I have log over dn. That's the depth, and I do something for every level. And then for every level, I have log 2 over d, and that is just, so I hope you know your logarithms laws, that's log n over log d times log d over log 2. Yeah, and that is just log n to the base of 2. Yeah, it just cancels out here. So exactly right what was said in the chat, and that's just the time for doing binary search of the leaves, right? So I could have, it's as good but also not better compared to binary search on the leaf. But here's an important thing. When you have big data, you're reading these things in blocks, maybe even from disk or from memory. And there's a whole lecture, and I can't recap that whole lecture, which is about cache efficiency and block operations. So you're reading, let me just very quickly what this is about. When you go to disk and you're reading just 1 byte, this takes a long time because you first have to locate that byte. And when you read that byte, because it took such a long time, you will always read a whole block, like 1,000 bytes. So you always read a whole block of things. And because you do that, and the same holds in memory, it's interesting how often do I have to read a new block of something. So the number of block operations, it's interesting. And here the number of block operations is just log d of n. So in a real database system, this d is not 3, but maybe 1,000 or 100 or 500 or something like this. So I'm starting my search here. This whole thing will be in a block. Imagine it's on disk. I read this whole block from disk in one single operation. I have to seek, read it. Now I have this inner node. Now I know, okay, where do I continue? Here. I read this thing here from disk as one block. Now I know I have to continue here. I read this thing. So I just have 1, 2, 3 times I have to seek. Seeking is expensive when you have large data. I have to seek, so wait on a hard disk, for example, if it has rotated under my head, 1, 2, 3. It's exactly the depth of the tree. And that's the point of this. And I hope that answers the question in the chat. And SQLite uses it as follows. Even if it has both, and I don't have a picture here, so you have to imagine it. Even if I have 2 tables, I want to join them on a column. Imagine I have a B tree on both columns, which we have done in the example. That's what create index does. What SQLite will do, let's imagine this is for one column and here's the other table. Now it will iterate over everything in that table, and for each element here it will just do a lookup here. Lookup, lookup, lookup. So iterating over one, looking up in the other. That's what it's doing. In a nutshell, there's a bit more. It can even say, oh, I'm not using this tree at all because it's so simple, I do some other things, but it's using the B plus tree as a lookup data structure. And if you go to, I don't want to go into that too much, I mentioned it, I think, in the last lecture, there was a link. If you go to the SQLite page, it said that this lookup is basically like a hash join, which is of course entirely wrong because this is a search tree. I mean, another way would be to compute, that's what we did in the last lecture, for these things, store them in a hash map, right? You can just, as key value pairs, store these in a hash map and then do a lookup. Do I have 34? And that's constant time. That's not constant time. So on the SQLite page, it somewhere says that a lookup in this data structure is like a hash lookup, which is, I think you can only say that if you have never visited algorithms data structure lecture. So, but there's more you can do with a B plus tree. So we have seen lookup, and it's very disk friendly, as I've explained to you. But you can do another, even simpler things. You can just iterate over the leaves, right? Let me just go back once more. You have these leaves now in blocks, so it's very easy to iterate over them because they're in sorted order. That's actually the first thing you do when you construct such a thing. It's what we did 2 slides back. We just sorted the whole thing. These are my leaves. And now I hope you remember what we see here, value, comma, row index, is exactly what we had in this lecture, lecture 5, slide 13. And it should be here. Let's just go to slide 13. This is what we had for the merge join, right? We had here value, comma, the row from which this value comes. This is exactly what we had. So here it's even for an example. I hope you remember that. So we are joining these 2 tables on course, and so we have value, so here it's a string, not a number, and row where it comes from, 3. Value, row where it comes from, even in the same colors as on this slide. And then you can do a merge, a zipper merge, like in the very first lecture. So if you have a B plus tree on both columns, you get exactly this, what we have in the last lecture. And if you have this, you should of course do a merge join, because it's much, much better than iterating over one thing and doing a lookup for everything on the left in one list, in the list on the right, right? This is linear time. The other thing is size of the one list times log size of the other list. And does SQLite do this? No. It never does this, even when it has a B plus tree for both join columns, which is just strange. Interesting, sorry, it's interesting. It's an interesting design decision. Merge join is not the most complicated thing to implement, but just so that it's clear, when you have a B plus tree, you get exactly what you need for the merge join. And every bigger, so SQLite is light, right? It's a light database system. Every bigger one will do that. So that's think about whether you have more questions. That's just some finer points or variations, closing remarks on this index on B plus tree. So one decision here we store value and the row index from where it comes. And let's go back even one more slide here. Right? This is what I'm storing in the leaves. The value, the thing on which I'm joining, and from which row it comes. I could also store the whole row here. Right? I could just store Mulholland Drive 2001 7.9. I could do that, and it has its advantages, namely, what's the advantage? If I do the join, and now I've computed, I do the zipper join over these things, then I immediately get the whole row of the result, right? Whereas in how we did it on the previous slide, I get the row index, and then I have to look up, okay, give me the row from that table. I have another indirection. So it gives me the full result immediately without indirection via the row index and looking that up. But of course you need more space, and because of that it's less I/O friendly. Let me show you that again. These things are really compact. If you now have a whole row here, you will have much fewer things in one block. And so this whole disk seeking thing will be more expensive again. And B-tree, are you listening? B-tree, as opposed to B plus tree, it just stores things also in the inner nodes. So here the inner nodes were different from the leaves, right? The data is only in the leaves, which means I can only go through the leaves. I have the whole data. And the inner nodes are just for navigating, for search, right? In a B tree, which is the older version, which is why it's not called plus, you also have this full information in the inner nodes, which has the slight advantage, that's the typical search tree thing. If I find something already here, then I can stop. Here I always have to go to the leaf level. But again, it's a similar problem. Now my leaves become much heavier. So I also have the row index here, or even the full data. So it's again worse for I/O excesses. And I'm duplicating stuff, right? Because this is already duplicating something. Now I'm also duplicating the 15. So there's a lot more to say about that, but I at least wanted to mention that. So that's why you typically don't use a B tree. I mean, these are design decisions, but yeah, think about it and ask if you have a question. Yes?
Why it's called a B tree if it's not binary?
Why is it called a B tree? Actually, I wanted to look that up, but I had so much to. You know why it's called a capital?
Just a guess.
Yeah.
Isn't there the A B tree? It always maintains at least A.
I don't think so. There's a B tree, yeah, but I'm.
Be an A B tree where A is 0.
Yeah. We have. Why is a B tree called B tree? No, what does the B in B tree mean? I wanted to look that up, so it's very appropriate that you asked. Does not have what? Bayer, Boeing, or balanced? I'm really okay. Rudolf Bayer, okay, a database guy from the past. Boeing, but their work was for Boeing. Okay, maybe. So he invented it and he thought, yeah? Yeah, Boeing says it's because of Boeing, of course. Yeah, I can imagine that. Yes?
Boeing research labs, it was developed and yeah. So
Yeah.
it says, if anything, the pistons for Boeing balance between broad, bushy and Bayer.
Okay, bushy, Bayer, yeah, it's bushy because it has more than, okay, so there were a lot of B words and they thought there's so many B properties, let's call it B tree. And here it says Stack Overflow, which is, gets no hits anymore because the AI answers everything, which is very sad, but a different topic. Bayer and McCrae never explained what, if anything, the B. Yeah, here we have even more. Okay, Boeing balanced. So, yeah, and it's interesting. So there are people who invented this thing. That's a different topic. I mean, a B tree is kind of obvious. If you think about it for 5 minutes, you implement a B tree. But there's always someone first in science. And because of human ego, it's very important to be first for some, or even if it's obvious. So a B tree really isn't something special. It's just a search tree with higher degree. And in practice, updates is a very big topic, and we just don't have time for that here. So what do you do if you insert a node? We briefly talked about that. There's a little part at the end where we'll talk about that. Okay, so that's there's so much more to say, but at least you understood the basics, I hope. Any questions about indexing before we now go to the even better stuff, which is automatic query planning. Okay, let's go to, and if you have a question in the break, ask it again. So, computing the optimal query plan, query optimization. What is this about? Let's just recap what we did in the last 2 lectures. It was even in the comments for the last sheet. Manual query planning is exhausting. So we have learned what a query plan is. It's this sequence of operations. You have your input table, says join this, then join this, select these columns, group it like this, project. Sequence of operations, you start with your input table, you get a result table in the end. We also saw, I didn't write it here, there are many ways to do that. That's also what the last 2 exercises were about, right? There's a choice. And to find the best one, we gave costs to query plan. So here's one, do the Cartesian product first, then select, or do it the other way around, it's cheaper. We learned to estimate these costs. So this is, and we did not only estimate the cost, but also the size. We have 2 tables here, we have an idea of their size, now we join them. Now we also need the estimate of the size of the result of the join. This is what we did for 2 lectures now. But now how do we actually choose between the query plans? We did that manually, right? In the lecture there were lots of, here's one way to do it, another way, and then you wrote it in code. You even outputted how much it costs and say, okay, this one is better. We never looked at all of them. And actually for a bigger query there are a lot of them. So this is just something we did not do so far, and this is what we will do now, and it's super interesting and quite sophisticated, and I hope you will like it. So we want to do that automatically. You have all possible ways to execute a query. There are a lot of them. Find the best one automatically. Here, just a little bit of terminology and assumptions. Let's only, there's group by, select, project, limit, order by, what not. We only consider joins. That's already interesting. That's the hard part. I have 5 joins. I can do them in a lot of different orders. That's hard enough, and it's actually the hardest problem of this whole find the best query plan thing. We'll just call our tables by capital letters, A, B, C, D, E, because we will draw join trees and we don't want movies, awards, person, it becomes too long. And we will write query plans as parenthesized expression, and like this. And this is actually easy to understand. It's like, think of an algebraic expression. This just means first join A and B. A, B are tables. I'm not even putting commas here or anything. If it's capital letters, it's easy enough to read. The more you put in there, join, comma, it becomes harder to read. I think even when you see it for the first time, it's clear what it's meant, right? First join A and B gives you a table. Join C and D gives you a table. Join these 2 together gives you a table. Join this with E. So I just write the 2 things which I join next to each other and put parentheses on the side. And this gives you a tree, but we will never look at trees now. We will only look at these parenthesized expressions, and we actually had them in lecture 4. I will come back to that, I think. So this is equivalent to, and let me just draw that tree here. So this is the tree A and B. And so I'm joining that, and the join symbol was this beautiful bow tie. And then there is C and D, which I'm joining. And this is just simple joins here. Now I'm joining these 2. And this is again a join. And you see this is much shorter than this. And then I'm joining this with E. And it's always a tree, because at the top I get one result. So, yeah. So this is, and as you can imagine, let's assume they can all be joined with each other. There's a lot of ways to join this, and each way corresponds to exactly one parenthesized expression. And that's actually a really interesting math problem. How many parenthesized expressions are there if you have n things? Let me just go back to lecture 4, slide Do we have it here? Just so, because I said that it's the same for, what did I say here, slide 18? Let me just find it here. Yeah, right, this is how we drew query plans here, and this is for a mathematical expression. I just didn't want to draw that again. It's the same thing. Yeah, you can draw every expression like this expression tree. It's a one-to-one correspondence. Any math whizzes here in the audience? How many ways to write a parenthesized expression with n things? There's a famous formula, a number for that? Does anybody know it? I don't cover it here, although I would love to. These are the Catalan numbers. So the Catalan numbers are, and does it even say no, I don't want, I do that, but not now. Yeah, here you have it, right? It's the open parenthesis, closing parenthesis. Actually, here you have it. And that's a math article, right? Here you see something very similar. A, B, C, D. It's actually almost our syntax. How many different ways can I do this? And that's just the Catalan number, Cn, Catalan numbers. And it has a super nice formula, which is here. That's the nth Catalan. It's a binomial coefficient. You can even compute it. And that's about the number of joins you can have if everything can be joined with each other. So super interesting math. Unfortunately, we don't have time for that. Query graph. Here I joined A and B, C and D and E. In a real join, I cannot join everything. I can only join certain tables with each other. They need to have a join column in common. Otherwise, it's the Cartesian product. So a very important thing is the join graph. And let's just put that, this is something I wanted to, it's also called a query graph, but I actually wanted, this I have to fix, sorry. And now it jumped away. Yeah, I will keep this as a minimum. I wanted to call it join graph, not query graph. And now movies contains movie ID, persons joins persons to roles and awards, but not to movies, awards. Let's just do the adjacency list first here maybe. So, and where do I write that? Maybe I write that here. So with which tables can A be joined? Can you figure it out you should know these tables by heart now. What's your guess? Let's just write the adjacency list. So for each table I want to know with which other table it can be joined. Yeah?
B, C, D, and E.
With B, C, D, and E? Okay, I think we should go very quickly to. So, this is the movies table. The only thing joinable here is the movie ID, right? Movie ID, do I have it in persons? No. Persons has person ID, but not movie ID. Do I have it in roles? Yes, in roles. Roles have a movie ID and a person ID. So from that, just thinking about where does a movie occur. Yes, please?
And roles and awards.
Roles and awards, thank you. C and D. So even if you haven't seen these tables before, you should. B can be joined with roles and movies, right? And awards, I think.
Movie directing.
I think A, C, and D, right? No, persons can be in a. Okay, now I'm confused. No, not with A, with C and D also. Please look it up. C can be joined, I mean, with A and B and with A and B, right? With anything else? Roles is just, I think. I think the roles are just, here we have them. It's just movie, person, and the name of the role. So it's not.
Awards also have person ID.
Awards has person ID. We will come. Oh, Yes, that's why B can be joined with D. And now we come to D.
But can rows also be joined with D?
Roles doesn't have award ID. This is roles. It has movie ID and person ID, but not. And awards just has. Oh, okay. Yeah, maybe you are right. I'm confusing myself. Thank you for asking. Yes? Yes, so it should be. Yeah, you are absolutely right. So C should also be joinable with D, right? And D, so you see it's not that easy. That's why there is a join graph. D, please, even if we get it wrong, it doesn't matter. It's just for explaining. What's D? Can be joined with?
A, B, C, and E.
That's too much. A, yeah, I think an award is for, we have to look it up. That's the awards. It has movie ID and person ID. So it's just A and B, right?
No, role also has a person ID and a award name as a award ID.
So, okay. Yeah, I'm really sorry. Oh yeah, we have, I see, yeah. So, oh my. So it's everything? Oh wow. A, B, C, and E, right? So the awards really, and the award names, I think they are simple, right? The award names it's just the names, it's just D. Okay. So I wasn't expecting that. Now we can, okay, we should have a break soon. Now we have to draw a graph, and we just have to draw a graph where just every node is a table and there's an edge if it can be joined. How do we do that now? Let me just, I don't know if I can draw this without crossings, probably not. A and B, so now we have C and both can be, yeah, I want to draw it without crossings, but I probably will not, so let me just A and I need a break too. Let me first draw C and D. C and D. Let me C and D. C and D do have an edge between them, right? C and D, and now both of them have. Maybe I can draw it like this. Both of them are connected to. A is connected to C and D, right? B can be joined with C and D. A cannot be joined with, it's not important whether I have a crossing here or not. D can be joined with E. That looks nice. What am I missing? D can be, D now has A, B, C, E. Am I missing so that's the join graph. Am I missing something? Please help me. E to D, D, A, B, C, D, E, C, D. I think that's it. Wow, I made it. Thank you. Thank you for your patience. That's the join graph. And you can see the join graph can be anything. Could also be everything's connected with each other, or nothing is connected with each other. It would be Cartesian product. We are not looking into that. Okay, that's the join graph, and it still says query. I have to fix that. And we are one more slide, then we're going into the break. So that's the join graph, and that's all the concepts we need now. Yeah, this is the cost. After that, we will go into the break. That's the cost function. So we somehow need size and cost estimates. We're just saying if we join two tables, the size is like the smaller table. Each row in the smaller table matches one row in the larger table. So we just take this. We already did that for the previous two ones. And now, here's a little difference. Maybe you already did that for the exercise sheet. The cost is now not only the cost for the join, but also the costs for everything before that. So it's the cost for the whole query plan. That's why I'm adding cost A and B here. So it's the cost for everything I needed to do to get A, which is already something complex maybe, everything for B, and the cost for the join. And we just say, we also did that earlier, the cost of the join is just the size of the result, just to make our life easy. And I think we should do that after the break. Let's have a break and then continue. 10 minutes break. Thank you. So let's very quickly we will now implement an automatic query plan together, which is really a planner, which is not easy. So some preparation work. Let's just compute the cost of some query plans using these size estimates, just for starters, just to some gymnastics. So here we have first AB and then C. So now we first have to compute the cost of AB and then AB joined with C. So we need 2 steps here just to get warmed up. So let's first do, actually this should be it's always better to compute the size first, because to compute the cost you need the size. So let me just swap these two. And sorry for the editing, I keep it to a minimum, but in this case I think it's good. So let's start here by computing the join of A and B. So what's the estimated size of A and B if table A has size 100? So initially, I can take the individual tables. I will also do that in the code as very simple query plans. It's just a table. You also did that for the exercise sheet. Like the operations at the bottom are just the tables. You just get them. It takes nothing to compute them. They are already there. But you have a size. You don't even have to estimate it. You know it exactly. So if I join A and B with these simple size estimates, what's the size estimate of the result? It's 100, yes. And let me even spell it out. Our size estimates are stupid, but they are better than nothing. They are very simple, and we will get something interesting already. And so what's the cost? And I'm using the shorthand notation here. I'm not writing the bow tie. So what's the cost of this join according to this? It's also 100. The cost for the tables, I just got them, that's free, and that's 0 plus 0 plus 100 equals to 100, yes? So that's 100. And let's now compute let's now do this. So what's this? This is now the minimum. Now I'm joining this thing with C, so it should be the minimum of the size of this 100 and 150, right? Yes. So the smaller of the two, and this is 100. And what's the cost? The cost that's the cost of computing the AB one, that's 100. What's the cost of computing C, just the table? 0. Yes, and the estimated size of the result, which is 100. So that's 200. And just a question before we go on, if I, and I'm not doing the math here, but let me just put it, if I, there's another query plan here, another possible one, which is first join B and C, and then join with A. Will it be the same, better or worse? Just try to do it in your head or have a feeling. What do you think with these estimates? What do you think and why? Yeah?
Worse, because the minimum between 200 and 150 is 150, and it's already larger than 100 we had with the
Yes, exactly. When I join B, let me just repeat it for everybody. When I join B and C first, they are larger. The minimum of the two is 150, and then the rest is the same. So, and what this tells us, that these estimates are good enough to realize, to understand that I should start with the smallest table, right? 100, because it will reduce the result. If I start with a larger one, then I will only reduce it towards the end. That's a recurring theme. We also had that in the last lectures. Don't start with the operation which produces a huge result. Start with an operation which reduces the result. And joining with A reduces the result. And we also don't do the math here. I could also do this one. I mean, assuming that it's joinable. If I do AC first and then with B, this would have the same, right? As long as I join with A first, it's good. That should have the same cost. But you can. So now a formula for the optimal cost. And I can already see now that we get slight time problems, but I've prepared a lot. But yeah, let's try our best. So how do we? Now comes. It's surprisingly easy to write down. We can define the cost. Robin, this should be blue. Can you take a note? I will not edit it. This formula is correct. I want the optimal cost for joining a certain subset of tables. And let's just say, for example, so for example, S is just the tables A, B, and C. Let's keep it simple, right? What's the optimal query plan for joining 3 tables? Let's just look at, and something is missing here. I'm taking all possible ways to split A, B, and C in 2 sets, because the last thing will be a join, right? So, for example, I could do S1 is A, and S2 is B and C. That would be one way to split it up. Or I could do S1 is B, and S2 is A and C. Of course, the question is, can I join this, and so on, and so on. So there are many possibilities to split this up in 2 sets, which I then join. And I just look at all of them. Look at this. This is a lot of symbols, but it's actually easy. I look at all ways to split up S, for which I want the best query plan, such that they don't intersect. I mean, I only want to join things with there shouldn't be a table in common, then it doesn't make sense to join them. Intersection is empty. They should give the whole thing. So it's a partition of A, B, and C in 2 subsets, and neither of them should be the empty set. So something like this here. And I just take all possible ways to do this, and for each way, what's the cost of the join? It's just, the cost of this one plus the cost of this one, plus the cost of doing the join, the optimal cost of doing this join operation. So I haven't, the cost star is just what one imagines. So this is, and why, this is a recursive formula, and I will have a slide just on recursion. This obviously ends because, this is really just looking at the last join I'm doing. It has to be something. This is all possible ways for the last join. Now I can plug in the recursive formula here. Why does it work? S1 is strictly smaller than S, so this will become smaller and smaller. S2 also, and this is something where I can just write the number. And it will be clear in the code, because we will essentially write it like that in code. Eventually we will, like every recursion, we will get to the bottom. The bottom here is where this set is just size 1, and for that we know the cost, it's 0. We just said the input tables have no cost. So the nice thing about recursive function is you can just write them as recursive functions in code, and it's really easy. So it's not, the only thing that's not trivial here is it's a minimum. You need a loop that gives you all subsets with these properties, all partitions of a set. We will also do that in code in a second. But just think about it. If I just implement this recursively, how well will it work? And let's first do something simpler. The classical recursive thing, it's the Fibonacci numbers. Let's just do them, and let's write a recursive program for the Fibonacci numbers just to check how good your intuition on recursion is. So let's just do that. And I hope you have seen the Fibonacci numbers before. So it starts with 0, 1. And the next one is just the sum of the first two. So what's the next number? 1. And the next one? 2. Next one? 3. 5. 8. And so on. You got it. That's the Fibonacci numbers. And now let's just implement them. And and I'm really curious. So Fibonacci, the hard part is knowing how many B's, N's, and C, and whether to put an H or not. So let's just Fibo, and yeah, there should always be time for Fibonacci, and let's just take N, int, and it will return an int. And how do I do it? Let me do assert. It only makes sense for greater or equal to 0, not for negative numbers. So recursion base, if it's 0 or 1, and please tell me if I make a mistake here, then it's just 0 or 1, right? That's easy. Otherwise, I just do the recursion. Then it's just, now I'm at least 2, so I can actually do what I now write. It's Fibonacci of n minus 1 plus Fibonacci of n minus 2. And now let's just write the import argparse thing here. Let me just write the obvious, and I think, let me just, so I want a parser. Yeah, that's good enough. I don't want a help function here. I'm just using a little help from because that's just boilerplate stuff, and I also don't need that. Yeah, so I just want parse the command line arguments. Yeah, so I can just enter a number, and then the nth Fibonacci number is this. Let's just try it. Python, that's the obvious implementation. 1, I should get, yeah, that's a good one. I think I should have written here n equals args n. Oh, my result is not defined. Yeah, here I should put Fibonacci. Yeah, let me write it like this. So, okay. What was the third Fibonacci number? Do you remember it? It starts with 0, 1, 2, 3, 4, 5. The fifth one is 5. You can always remember that. Fifth one is 5. The sixth one is 8. Fine. 10th, 55. It works. The recursive works perfectly. 30th number, it works fine. 50th number. What did we do? Did we have an infinite loop or something? Now your intuition. Okay, I have to ask somebody else. Yanni knows it. What's going on? Worked fine for 30. I mean, this is computer scientist induction is if it works for 1, 2, 3, 30, it works, but something breaks. Is it 42 thing or? Mm-hmm. Yeah, exactly. You are calculating the Fibonacci number, for example, of 2 a lot of time. If you write, that's what he said, if you write the computation as a tree, it's a binary tree, right? And what's actually, if it's a binary tree of depth 10, how many things do I compute? 2 to the n? Yeah, but something like 2 to the n is exponential, right? For the next number, it's twice as much, and actually, as so happens, reasonably fast. I'm commuted. Commuting is also bad, but computing is even worse. So it's 2 to the n. Let's just do very quickly. let's just do the, so this is the recursive thing. And let's just do the iterative thing, just to, because that's also what we Fibonacci iterative. How do we do it iterative? That should also be easy. Yeah, so we, yeah, if n less or equal 2, we can just, yeah, let's just use the recursive one. That's good enough for, we don't have to do the assert one. Otherwise, we just, what do we do for I in, yeah, let me just do, so previous is, let's start with 0, current is 1, for I in, now I have to, you have to tell, is it 2n? So what do I do? The next is, okay, next is a keyword. Next is previous plus current. I could write this simpler, but I just want to make it more clear. So the new current is the previous, and the current is the next. Yeah, I always remember the last two. Is this not correct?
20 and 21 are not reasonable.
What is not reasonable?
20 and 21.
You don't, okay. I hope we don't spend too much time on iterative Fibonacci. You don't think it's correct? So the next one is previous plus current?
Previous should be current.
Where?
920?
Previous current is equal current?
No, previous is equal to current.
Oh, previous should be current. Yes, I agree. Previous. We can just try out all combinations. One of them will work. Now oh my, what happened now? In line 30?
1, 3.
1, 3, 13. Oh yeah, this will break everything. Let's just try it. Maybe we are lucky. Fibonacci iterative n. And let's see if 5 is, oh, this is still running. Is there still a mistake? Yes. Oh, yeah, it should have been result here, exactly. So this one should be iterative, and this one should be result, right? So let's check 5. If 5 is 5, okay, that's bad. What did we do wrong? Current is, probably it should have just run. Yeah, it's a one-off mistake, so you just try all combinations, right? So 5 is, if 6 is 8, it will be correct. Okay, let's do 30. Okay, not bad. 50, that's a bit faster. 100, okay. Okay, and we want comma separated. If you have, this is really important, if you work for us, large numbers should always be printed with separated by commas, otherwise you can't see them. 100, 1000, 10,000, okay, not, iterative is a bit faster, yeah? It's linear time, even for Python, summing up 10,000 numbers is not a big deal. 50,000, eventually it will break because I think the internal, yeah. 40,000, okay, yeah, we can, okay. You get the idea. So that's really important when you have recursive formulas, you must not implement them recursively, right? Otherwise terrible things can happen. Sometimes you can, here you can't. This would now again be a slight detour, we're not doing it, it would be 2 to the n. And we just implemented it in linear time. So now, that's, I hope we can do it in 20 minutes, is we just want to implement this function iteratively, and we will do it together now with your help. Sorry, this function, I want to compute it iteratively. Remember it, and now is a slide how to do it, and then we will code it. So we start with all singleton query plans, one for each of the input tables. And before I go on, let's just go to the code and do that. Let's just go to the code now, and because I think it's super instructive to do this together, and so I have a little bit of preparation here, but not too much. So query plan, I need a class for my query plans. And for those of you who did the exercise sheet, the query plans are actually trees. It was actually operation, and an operation has another operation as children, so implicitly there was a tree. We don't want to do any of that now. We want to have it simple. We want to concentrate on the query optimization. So I will just write my query plans like this, and it was on the slides before, right? Join A and B, join that with C. Actually, we didn't write the parentheses about the singletons, so we even wrote it like this, right? So this is the query plan that first joins A and B, and then the result with C. And we also have to know which tables are actually being joined so that we can check disjointness. So, and we can do that very simply. We just store the sequence of capital letters. So I'm making my life really simple here, not real table names, just capital letters, and I write my query plans like this. I don't care which columns are being joined. I just want to reduce it to the core for this problem. So this is what I'm storing, the plan. This is just this thing here. It's a parenthesized expression. I think you have understood it. The tables, this is just ABC. And I just remove all the parentheses and sort it. And why do I sort it? Because I just want to know which tables are these. And for two plans joining the same set of tables, it should be the same thing. So that's an easy way to get this. It's sorted. If I have another plan which does A and C first and then B, it will also have A, B, C. It's just a simple way. And then I have the cost and the size estimate. Okay, and the first thing to do is maybe, let's maybe do that. Let's write that here. So how do I, so I have a new plan now. How do I create a new plan? Like, maybe I write it just like this. So my new plan, if I can join them, is just, I'm just writing like this. I'm writing parentheses, and now I'm writing, is it that simple? I'm just confused. It's the plan of the first plan, and is that correct? And then I'm writing, I think it is, yeah. So that's just how I write a join. I write them next to each other and put, you don't agree?
There should be a curly brace where there is parentheses.
Yeah, that's true. There should be a curly brace here. Oh my. The curly brace does things in my... that was... okay, that's the plan, and let's do the size. The size was just the minimum, right, of the two sizes. Is it min? Plan 1 dot... Yeah, please help me. Robin, can you also check and just help me with these little things so that we don't lose time with this? I think it was just the minimum of the two sizes. And then, and that's it. And the cost is just, that was just the sum of the costs, right? Plan 1, cost plus the size, exactly. And I'm taking this a little slow so that we... And then I just return this query plan, which is just, here's the constructor, right? It's just query plan of plan cost size. It's in that order. Maybe the other order would have been better, but okay. This is just creating a query plan from two query plans. I'm just writing them next to each other, and this is... and it will be nice for output. This is our cost function here. Okay. Now let's, this is our join graph. Let's go to the join graph later. Let's maybe go to my, let me go to my main function. I have to explain a little bit of infrastructure here. So I'm starting, my input tables I'm just hard coding them here, no query or anything. I'm starting with 5 tables, A, B, C, D, E. And they have these are my initial query plans, right? A single table is also a query plan, was also like that in the other exercise sheet. No cost to compute it, it's just there, and I have some random sizes here. I just picked some sizes which are different. And I have a join graph here. I will come back to that join graph. I just need some join graph. I will come back to that. Let's do the first round of the query planning. And where's my query planner graph? So I'm I'm going in rounds, and in the first round I just start with these singleton query plans, and I just wanted to, in the first round, let me just write that here, start with the singleton query plans. Singleton means each query plan is just so I'm storing all my optimal plans in a hash map, and now I'm just the optimal plans of size 1. I store them like this, optimal plans 1, and initially it's empty. This will become clearer in a second. And now what do I do for... So here my input plans, I give them in the... So for plan in input plans, colon, let me just... And I do it as follows. Optimal plans 1. The 1 is input plans for one table, for joining one table together. In the first rounds, I have just plans which join one table together, which is just those. So 1 of, and now I use the tables as the key here, and this should be the plan. So this is now just A or B or C. It's just singletons. And let's just output them. Let me just print. What do I print? Optimal plans of size with one table. With one table, let me write it like this. And now I just output all of them. So for, actually I can just do it in the same loop and print it here. So that's my, and now I just want to print them. It's a little bit slow, so but that way you can get used to the code. So the table is, what is the table? I want a formatted string. These are my table is okay, something happened here. I don't have a light when this is plan.tables. It's the tables of the plan, but I'm in the first round, so it's actually just a simple table, and the size, I don't have to write the cost because it's just simple tables. Size equal, and here I write plan.size. Okay, and let me do that. Let me just run it just to see what... There's a self, you are certainly right. Thank you for paying attention. In self input plans, anywhere else? Yeah, okay. Thank you for paying attention, and let's just execute it. Query planning.py. Yeah. So these are the tables we start with, table A, B, C, D, E, and they have these sizes. So that's our first round. That's the first round of, and now comes the next round, and we have to now in the second round we compute the post. Now this should be round 2, not round K. K comes later. So round I is computing all optimal query plans for everything that joins I table together. So in the second round, everything that joins two tables together. And in the kth round, it's everything that joins k tables together. And this we do recursively now. And this is just for reference. Let's do this now. And now pay attention. This is the so in round I, compute, and so for, in round, maybe I said it's round k, so for k in, and for now let's just do the second round, and let's figure out in a second how many rounds we have. Let's just do the second round. So now we have 2, and now we have to figure out all ways of splitting 2 in 2 smaller sets, and there's just one way, but let's do it more generally right away. So we look at all ways for k in, for k1 in range 1, comma, let's maybe do it that way, and then k2 equals k minus k1. Now for round 2, this should just be the only combinations which make sense are 1 and 1. The only thing I can split a set of size 2 in 2 smaller sizes is one set 1 and the other is also 1, if none of them should be empty, and they should give the whole thing in a disjoint way. That's what we had earlier. So this should also work for larger case here. So this, the only thing this loop here generates is k1 is equal to 1 and k2 is equal to 1. And about this k thing, we have to, whether that's really correct, let's check. So now we have to combine anything of size 1 with something else of size 1. And we already have the query plans of size 1. They are here. We stored them in optimal plans in brackets 1. So let's just, so for, and I hope that's correct, so for all possible plans of this size, k1, for plan 1 in optimal plans k1, and I'm also iterating over, and you see it's I'm already 4 levels deep. It's not really hard, but you have to get, but let's take it slowly, and I hope it's correct. So now I have, now inside here, I have all combinations of smaller plans which I can combine. And now let's just,
That's missing optimal plans.
thank you. Thank you for paying attention. Now we have to compute whether they are actually joinable. And let's do that in a minute. Let's just say for now it's true. So if joinable, let's just join all of them, just to write the rest of the code here. So if joinable, then what do we do? Well, then I think the new plan is, we just had this, we just wrote this before, right? Now I'm just joining them here. It's the query plan join method, which gives me a new query plan. So that's, so this is, and it's a static method, so I'm not, so it's join plan 1, comma, plan 2. So now I have a new plan for this particular, for these 2 subsets of size. And this is now for 2 tables. Now I have to make sure, maybe I already have other plans for this table. So if plan tables not in, the first thing I think I have to do here is now I have to start a new dictionary for this. This is now all my optimal plans of size 2. So if this is not in, if I've not seen this set of tables before, If not in optimal plans K, then optimal plans K So when do I store this? If either this is not there or it's already there but it's better, or plan cost is smaller than one optimal plan which is already there in K for either it's already I will explain it again in a second, but I think that's it. That's already the end of the loop, and I think I have to format this a little bit better. Then optimal plan dot tables is equal to plan. I claim that that's it. So if I have a new plan, let's say it's a new plan which joins A and C together. Now I have to check is either this, I've not had a plan so far which joins A and C together. It's of size 2 here in this case, or I've seen one already and this one has better cost. And this should be cost here, right? So I hope this is, and now let's print them, so compute all optimal plans of K tables, that's what I'm doing here, and now show all optimal plans of K tables. I hope it's just a little longer. We've written most of the codes, please. So let me just optimal plans with, and this should be now K tables. K tables. And now we have to go down, we just go over all 4 plan in optimal plans of K. And now we just output like above, I guess, print F. Yeah, the tables are now plan.tables. This should now in the second round only be tables with 2. Just a second. Might well be. This should of course be these things. And now here we write the cost and let's write the size. And let me maybe write it like this. F equal size, and this size should be the, what did it do now? Plan dot size, plan dot cost, yeah. Do you have, yes, you have a question? Something wrong?
Line 109, you wrote print K, but it should be print F. And then you missed the comma in line 101.
In 101 I missed a comma.
Line 111, I think. Or?
111?
No, man.
Okay. Let's just run it. Str object in line 35. What have I done wrong? Oh. We are almost done. Plan 1, plan 2, plan. Where did I call it? In line 102. I did something wrong here. What did I do wrong here? These are 2.
If you didn't initially create in line 90, you didn't create a query plan initially, but instead you just assigned plan.
What do you mean? I didn't create one?
Line 90.
In line 90, I did not do what?
You do assign a string, but you should have assigned a query plan, right?
Oh, here? That's a query plan. The input plans are plans. Bear with me, this last hurdle. I'm sorry for the overtime. I will make up for it. Let's find this. This is... So what does it say here? Str has no attribute plan. So it says plan 1 is okay. That's so K1 and K2 here. Let's just print them for... I mean, they should both be 1 and 1, right? Yes, they are 1 and 1. It's just, yeah, the ones with... So why in optimal plans don't I have... Did I not? These are query plans, right? A is a query plan, and I just put in here don't you agree? I put in 5 query plans here in the query planner.
Can you print optimal plans? Can you print optimal plans?
Optimal plans of 1. Yeah, but here I put in plan and... Oh, I know what it is. Come on. This should be values. This is a hash map, so I have the items now. Okay, we made some. Has no, plain tables. It's the same here. Yes, so here I have, so now I have all combinations of, that's because I said joinable. So now I'm just having all combinations here. We're almost there, really. And we will skip the slides after that, because they are there for informational. Now the only thing we need, that's really easy, we have to do, so we have our join graph. So the join graph here is just the adjacency list we have seen earlier. That's a star. Everything can be joined with A, but not with each other. So A can be joined with everything. Everything can just be joined with A. If you draw that as a graph, it's a star. Doesn't matter, it's just our example query plan. Now we have to compute, can 2 plans be joined? 2 things have to be checked. It's really easy. Are they disjoint? No tables in common. So let's just, tables, let me deactivate that, tables disjoint. How can I do that? I just make a set of the tables of the first one, and then I think I just write is disjoint of this one, yeah? And now the next thing I need to do is, can they be joined? Is there an edge in a query graph, right? Edge exists. Well, and that I just do a for loop over both of them. So for table in plan 1 tables colon table 1 in plan 1 dot tables for table 2 in plan 2 dot tables. And then I check whether it exists in the adjacency list. Yeah, I don't want this one here, table 1. And if it's, so I'm just checking, I'm just doing the full loop, and I'm checking is the one in the adjacency list of the others, and then I just return, So if they are just disjoint and there is an edge between them, then I can do it. And now I can just call this function, and now it should just work. I hope we are done now. Joinable. So actually, if, how do I, it should be self, join graph, joinable, plan 1, plan 2. Now I should only get the ones which are joinable. AB, AC, makes sense. Everything is only joinable with A. And now, if I'm lucky, let's just do it for 3 as well. Yeah. Now it just goes on like this. So with 3 tables, now it will just for ABC look at all ways to split this up in 1 and 2 tables. That's the only ways here. How? You tell me. what's the, okay, it suggested it here, it's the number of, I should go up to the number of input plans. I want to join for 5 tables in the end, if it's 5. Let's just do it here. And that's it. So the second round was the hardest. So I will give you this code and the exercise sheet, and that's it, really. You don't need anything more. The last part, anyway, let me just, to show you that I was expecting this. So the last part is purely informational, and here's the proof. This is the proof. This is not Klausurelefant, okay? It's not elephant for the exam. So the last 5 slides, I just wanted to mention them because you might ask why are we not dealing with it. But I wanted to show you the exercise sheet now. Exercise 1 you should absolutely do because it's a typical exam question. Just 1 more minute. I'm sorry, but this 1 minute. Just run this algorithm yourself. You absolutely have to do it to understand this. We just coded this. Just do it, and do it actually for the example query graph from the join graph from the lecture. Just run it yourself. Be the algorithm and do these things. Divide it in all sets, do it on paper. That's the best way, and I say it's the only way to understand this. Do it yourself and check it against this code whether it's actually correct. Maybe you made a slight mistake here. You will find it. That's exercise 1. It's the best exercise to understand it. Play this algorithm yourself. We have coded it together. I will give you the code. And then the second exercise is integrate it with your code. Robin has prepared a lot of code. You don't have to do the parsing or anything. He gives you the join graph, it's already computed from the query, and then you just write the optimizer, either for the master solution or your last exercise sheet. And then you have a database system which does automatic query planning. Any quick question? I'm sorry for the overtime. I knew it was going to be hard. Please do exercise 1 at least. Everybody must do exercise 1, otherwise you won't. No? Okay, thank you very much. Oh, we have a quick one, sorry, a very quick one.
So,
yeah?
Fibonacci can also be computed efficiently using dynamic programming by storing previous results.
That's what we did, yes?
Yes, but we did in an iterative manner. Can we also implement query planning recursively with memorization? Shouldn't that look prettier?
Okay, that's a pretty sophisticated question. Can we compute it recursively with memorization? I don't, yes and no, but we should take it offline. It's a very good question. Thank you. Please do exercise 1. See you next week. Bye-bye.